Oh, we're back. We're back. Coding on Twitch. Today, our project is working on rewriting zlib in Zig. And today's topic is looking at back references in the way, and like the zlib data packets. So, our current understanding is something along the lines of you have object, you want to compress it. You run it through zlib, which is like doing something very similar to like other compression mechanisms, right? Like zips are going to be doing something very similar under the hood. Zlib goes, hey, I'm going to write you like this like little header over here, and this says I'm zlib, and this is kind of like how much data I expect you to have, and maybe it doesn't even say that. Maybe it just says I'm going to be compressing you with deflate, the deflate algorithm. Let's double check. Zlib Wikipedia. So, okay, it's not going to be, I'm not going to get this immediately, and it's not worth talking about. So, under the hood, he's using this thing called, like, deflate. And the way deflate works is he's got, like, chunks of data, blocks, I think they call them, and there are a few types. One of them is, like, no compression. And the idea is that, like, maybe you have something that's already, like, well compressed or high entropy, and so there's really no point in doing anything extra to it. Like, you're not going to get better than what's already in there. So this is basically just saying like length plus data, and then you just copy that shit into your output. Then there's these other blocks that are using Huffman encoding. Huffman coding. There's like a couple variations of these guys. One of them is using this like pre-agreed upon dictionary, we'll call it for now. And the other one is like it embeds the dictionary up front. And the idea behind this like Huffman coding is that if you have like some text that has like high frequency of one character and low frequencies of another, so maybe you have like lots of A's, a few B's, a single C, and a single D, you can encode this in a way where like the A's take up the least amount of bits, the B's take up the second least, and C and D take up the most. And so they store it in like this like kind of tree format where they go like A is here, B is here, C and D is here, and we've kind of like written some code to try generating this, where you basically take like the least frequent things and you like pair them up, and then you just like pair up things until you end up with like this tree, starting with like least frequent over and over again. So you like the sum of these guys becomes like a new node, some of this whole thing becomes a new node, etc. And you can like walk this tree and say, well, if I go to the left here, this is 0. If I go right here, it's a 1. 0, 1, 0, 1. And then you can like look at these branches that you're taking and like use these as a value, right? So you can say that the A is you take one left step. A B is you take a 1 right step, then a 1 left step. C is right, right, left. And D is right, right, right. And you end up with this like encoding where things that are used least frequently require the most amount of bits. Great. So we've kind of like decoded that as well, so that's kind of working. But the catch here is that the zlib or deflate, he has values for every character in the range of like 0 to 255, right? This is like your typical uint8 amount of data. But this tree doesn't really necessarily have to go to only 255 values. You can go to like more. And so what they do is they have these special values. I think it's 257 to 285 to 285. And these guys are like special values that essentially say, hey, could you go back to something that you wrote down before and write it down again? And so I want to take a look today at trying to figure out like, how do we parse these values and how do we handle them? So plan of action is approximately try to figure out try to prove to ourselves that we understand the format, right? So maybe we can like generate a block by hand and try to decompress it with the official zlib library. Official doesn't really mean anything in open source. Like the real zlib library, we'll call it. And if we manage to get a block that decompresses successfully, then we've proven to ourselves that we understand what the format is supposed to be, and then we can try to decode that ourselves by like figuring out what these back references are actually saying. And then once we know what they're saying, we need to like have like a ring buffer of previously data that we've decompressed so that we can reference it and copy it back into the new stream. Easy peasy. So that's the plan. That's the plan. I think we just hop in. We're 5 minutes into stream. Generate test block and decode. Okay. So we have some sample blocks that we've generated already. We have one that we generate a no compression block. And then we have one and we generate one that uses like a static Huffman tree. And I guess what we can do is maybe we'll generate, I guess in this generate zlib with static Huffman, what we could do is we could try to detect certain cases, like certain data patterns, and try to use back references to implement them. Because we could hard code some data here, but it'd be kind of nice to keep the behavior of like our sample program right now. Not zig build and this. We allow ourselves to like input any data and then see how well it gets compressed. So it'd be kind of nice to keep using this like test input as our test. So I think maybe what we do here is maybe we look for one of the things that this thing can do is like duplicated letters. So let's see. Because here, if I understand what I've read correctly, when we read in a value, he says, "Hey, this is how long I want you to copy for," and then you read this like extra bits field. And he says, okay, read this many bits to get the distance. And you say from here, oh, okay, here is how far back I'm copying from. And a key thing to notice here is that a lot of these extra bits fields are 0. And you're like, okay, so I have a length and no distance. What the fuck does that mean? And I think, if I've understood correctly, I think what it means is you have like some decoded stream. You've written like, hello. And if you're like right here and you're decoding the next byte, and he's the value 257, for example, I think what this means is he's saying copy 0 bits back or 0 bytes backwards from where we are 3 times. So we say, okay, well, where are we 0 bytes back? There's an O here. And if we were to copy 0 bytes back 3 times, we would like copy the O in, and then we would like move our pointer forwards. And then we go like, oh, there's another O here. Okay, we'll copy that in. And then you move your pointer forwards, you'd be like, oh, I see another O again. And you stick another O in. And so you can like technically copy past the end of your buffer as long as you are kind of like duplicating things that you have before. So you could do something similar where you have, say you were to copy, like, say we had something like, I guess they don't have the ability to copy 2 bytes back, but if you could imagine a scenario where you went to the L and you said copy 8 times, you would end up with like LO, 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 because you're like basically repeating what you see. You're like taking the part you're copying into and using that to generate more data. So the first test we could do is we could just test basically looking for like this double L in hello. And maybe we could use that to encode something like this. I guess 2 L's isn't one of the options here, if I'm understanding this table correctly. But 3 L's would be. Yeah, so what we can do is we can maybe... Let's see. So we have data. He's coming in as like a string. And we could basically write out a new chunk of data containing a back reference if we see something that makes sense. Let me look at this. Let me just look at this one more time. I want to see if I'm missing something obvious about being able to encode any types of back references, or if there's like specific ones that we can't do. So we can have like the minimum length is 3, and we can copy up to 10. Here, if we pushed in 265, we would have to copy 11 bytes, it looks like. 11 or 12? I feel like I'm misunderstanding something. Because here, if he's saying, hey, you could be 11 or 12, and you read one more bit to get that value, that makes sense to me. But then, is it that distance? Was my understanding about distance wrong, maybe? It could be that it's always length then distance. The extra bits could be only related to the length field itself. That would make more sense to me. And then I just have to assume that I'm going to read a distance after. I think that makes sense. So say I got the value... hold on. Encoded data blocks in the deflate format consist of sequences of symbols drawn from 3 conceptually distinct alphabets, literal bytes, or length backward distance pair, where the length is drawn from 3 to 258, and the distance is drawn from 1 to 32,000. In fact, the literal and length alphabets are merged into a single alphabet, 0 to 285. Yep, where 256 indicates in a block, values 257 to 285 represent length codes. Okay, so I understand the values 257 to 285. These now get mapped to these length codes. Does that mean that after that I just parse a distance code, like immediately? And then the pointer is like, maybe I'm like sitting here, 1 past the last letter read. And so distance 1 means the last character. That seems possible. So these codes go 0 to 29. And what's like the data format here? So 29, does that mean I have to read 5 bits? That doesn't make sense. That doesn't make sense. Maybe the deflate Wikipedia article will give us a better clue. Within compressed blocks, if a duplicate series of bytes is spotted, a back reference is inserted, linking to the previous location of that identical string instead. An encoded match to earlier string consists of 8-bit length, an 8-bit length, okay, and a 15-bit distance to the beginning. If the distance is less than the length, the duplicate overlaps itself, blah, blah, blah. Searching. Okay, so how is it like encoded? That's what I want to understand. Bit reduction. 257 to 285 combined with extra bits, a match length of 3 to 258 bytes. Okay, so how do we get the distances? A match length code will always be followed by a distance code. Based off the distance code read, further extra bits may be read in order to produce the final distance. The distance tree contains space for 32 symbols. Oh, they're saying distance tree. I wonder if like the distance is also Huffman coded. But they don't talk about like how many bits. The 2 codes, the 288 symbol length tree and the 32 symbol distance tree are themselves coded as canonical Huffman codes by giving the bit length of the code for each symbol. Ah, okay. The bit length of the code for each symbol. The bit lengths themselves are run length encoded to produce as compact a representation as possible. As an alternative to including the tree position, the static tree option provides standard fixed Huffman trees. The compressed size using the static trees can be computed using the same statistics as used to generate the dynamic tree. So it's easy for a compressor to choose whichever is smaller. Okay, so where is the the static tree then? Where is the static tree? Blah, blah, blah. None of this. Not this. Compressed blocks. Compression with Huffman. Okay. The Huffman codes for the 2 alphabets are fixed. Blah, blah, blah. So we've already parsed this tree. We have this one already. The code lengths are sufficient to generate the actual codes. Yep, because of canonical Huffman encoding. Literal length values 286, 287 will never actually occur. Distance codes 0 to 31 are represented by fixed length 5-bit codes. Oh, okay. Sure. So this is the part I'm missing. Okay. So we get the length out of this tree. We might have to read some extra bits in order to get the right value out. And then we get the distance code, I think. That would make sense to me. Okay, so let's just try. We will try Maybe what we'll do for now is just at the end of the input data, we'll insert a back reference unconditionally. Yeah. That then we don't have to do any like intelligent search or anything. We can just do it by hand. So we can do something like 256 is end of block. So let's try doing something like we can Huffman code in the value 257. Let's just start there. So we put in 257, and then we need a distance thing as well. But the distance is not Huffman coded. They are just fixed 5-bit codes. Fixed length, yeah, so not Huffman coded, pretty sure. So here we say something like we use our Huffman writer and we write in just like a U16 array, kind of a single value of 257. Okay, and then how does this Huffman writer write work? We have to like look at his underlying bit writer, which we can do. So I think we just go Huffman writer write bits. And we're just going to write a 5-bit value, which in this case is going to be 0. Then we write our Huffman coded end sequence and finish. And if I understand that what we've done correctly, we should get a character at the end of our thing repeated 3 times. So we should see hello world. We're trying to encode hello world, and we should say hello world. Unreachable code at bitwriter at line 38. So probably he doesn't like us manually writing the number 0 here. Yeah, he doesn't like that. So we probably have to say like as U32 or something, as U8. Doesn't really matter. Just Zig has to know the like right type here. So zlib decompressed. Custom zlib decompressor. Oh, okay, so we need to run some code to run this through our zlib decompressor, or the real zlib decompressor. So maybe we do something like demo custom Huffman block. And here we're going to take in an allocator and an input. And we're going to return nothing. And I guess it's going to look similar to this. We're going to generate our static coded Huffman block. I guess we can just do it here. We generate our Huffman encoded block with a static tree. And then here, what we should do is we can just instantiate, we can try to decompress it with like a real zlib. And then here we can say static Huffman block contained. Here we'll change the log to say custom decompressor found this. And we'll say real decompressor found this. Yes. All of this, I think, is making sense. So we can say decompress with zlib. And we have our input data, which is the buffer from 0 to bytes written. And we have an output buffer. So I guess we can just use the same output buffer. This is going to fail. And that's just okay. So what I'm going to do here is I'm going to put a 0. I'm going to make an array of size 1 of U8s with a 0 in it, and then multiply this by 4096. And I think this gives me an array of 4096 elements that are all zeroed out, which means that there's a null terminator. So however far we write, if we try to print the string after, we'll just get up until the first null terminator. Fine. Here, this is going to fail because our custom generated blocks don't have like a checksum at the end like zlib expects. So we're going to say catch fuck off, essentially. Okay. I think probably need an ampersand here. And he doesn't like that, actually. Sig build. What is he complaining about? Expected semicolon. Sure, okay. And then discard of error capture. Omit it instead. Sure, okay. And then use of undeclared identifier read bytes. Read bytes. This is bytes written, I guess? Oh, no. Here we just print the whole thing. And then I think we're chilling. Zig, build, run. Zig, build, and run. Incompatible types, use size, and void. Right, so we have to kind of discard some stuff here. Where did we go? What the hell? It's here. Discard. Discard, discard, discard. Okay. Real decompressor found hello world with 3 Ds at the end. So that's a really good sign. That means that we at least understand this 257 and this thing. Now, let's see, could we try to go back some amount and maybe pick some data instead of the D? What if we were to try to copy like an O or something? Hello. Like we have, where is it? Hello world. So if we wanted to copy the O, we would have to go back 1, 2, 3, 4. So that's just we write a 3 here instead. And if we understand that correctly, then we should see hello world do. Real decompressor found hello world. So that's not right. This didn't work. So if we just write a 0 here, that's fine. That does what we expect. What if we write a 1 here? Here we get... Oh, not this one. Okay, so there's something about writing bits here that isn't doing what I expect. And I think actually probably what it is write bits might be like copying some value directly in. Like you can imagine, how do I say this? So if we have bytes packed into an array, right? You have like A, B, C, D. This is actually maybe like a bunch of bits in a thing. 0B, 0, 0, 0, 0, 1, 1, 1, 1 or something. It doesn't really matter. When we say write bits, the number 1, 5, it depends. Like I don't know if the decompressor is expecting that if I were to write 0B, 0, 1, 1, 1, 1, right? Does it want me to write that this way or this way? Or like, am I reading right to left or left to right? Where right to left and left to right are like kind of poorly defined because like bits aren't really ordered in a byte, but like the way we might need to swap bit order essentially. That seems possible because otherwise, like, I don't know why this would work as I expect, but this would not, unless that it's like going backwards. I remember hearing that numbers need to be encoded backwards. Yeah, it definitely seems possible because like somewhere in this spec, they say that they expect to read least significant bit to most significant bit. So if you were reading 1 bit at a time and you had 0B 0 1 1 1 1 and you read 1 bit at a time, you would get 1 1 1 1 0. And depending on how the decompressor expects to reconstruct that, I might need to write this in a different order essentially. So here I have some code already to do like this bit reverse. Let's just like pull it out into a function. So we can say pub function bit reverse, and we have some value which is any type really. We don't really care what it is. It's some numeric type. And then we have num bits, which I guess we'll make a usize. I don't think it really matters. And we'll punch out the same value we got in, which kind of means that we need this to be we need to take in the type as a parameter. And the val is a t, and we export a t. Oops, what the fuck just happened? Okay. And then we return this thing. So bit reverse val, int cast, val, blah, blah, blah. And there's some use of self in here, so boom. Okay. And then here, we're just going to replace this guy with bit reverse self u64 self val self num bits. Okay. So now I should be able to go here and say I want a bit Huffman bit reverse, and I want a U8, and the value I want to write is 1, but I want him reversed with 5 bits, and then I want to write those 5 bits. Yeah. Let's just see if that does something more like what I want. Okay, so that's a good sign. So now I'm seeing LD, LDL. So that's saying, you could also return type of val. Oh yeah, that makes more sense. I like that better. So here I want to say val is an any type, and here I want to return a type of val, and then I don't need to fucking pass in this U8 here when I don't want to. Although I still need to write as U8 here because things taking any types need to, like the compile time integer doesn't really have a fixed width, and so you have to kind of like say when you're using things that use fixed width that like this is what I expect you to have, blah blah blah. Okay. Cool. So yeah, so here I'm saying go back 1 character from the end and write 3 bytes, and we did that. We went LD, LDL. Perfect. Cool. And so if we wanted to get crazy with it, we could try going even farther. So let's try doing something that requires an extra bit. Let's try going maybe like 6 back. And so he's going to read the first 5 bits, and then he's going to add that to 1 more bit, I guess. Let me think about this. I guess we're going to have have a table somewhere of these guys. I think that's the only way this is going to make sense. Because I don't know if there's any obvious mapping here. So the number 4 getting turned into 5, and the number 7 getting turned into 13. It kind of is related to how many of these guys use extra bits for each type. I think that I think we just need to use the table. I could be wrong here. 1, 2, 3, 4, 5, 6, 7, 8, 9 to 12, 13 to 16. Yeah, I'm just gonna stick this shit in the table. Even if it's possible, I just don't want to. I don't want to worry about it. I just want to double check here. Let me just do a little bit of quick math. Python? Ugh. Python, please hit me with it. Okay, so let's say here at the end, we have code 29, which starts at 24577. I just want to double check that if I add this plus 2 to the power of 13, is that the end of the range? 32768, 32769. Yeah, okay. So our table is going to have, our distance table is going to say, you read some value, code, and here is your starting value, and here's how many bits you need to read. And then the encoding is just going to be start value plus next thing. I think that makes sense. So let's make some more room for ourselves, and maybe we'll just put it struct distance. Distance. What do we want to call this? Distance table item, I guess. It doesn't really fucking matter. In here, each element is going to have the code, but the code is going to be like, if we stored an array of these things, the code is kind of like implicitly the index in the array. So all we need to store in here is extra bits, which is going to be, I don't know, use size is like overkill, but who fucking cares? I wonder if it can be a comp time int. That'd be kind of cool to like guarantee that these things are generated at compile time. I don't really know how that's going to work out, and so I want to try it. And then we can have the offset, or range start, we'll call it. Okay. Then we can say that we have a distance table. And I guess he is an array. Is there like a Zig kind of expected format for global variables? I think I've just seen him as like just regular camel case. I think in stud testing, there's an allocator. Yeah, they just have pub const allocator lowercase and then allocator instance. Yeah. Okay. So here, I could just want to do const distance table is equal to an array of 29 values, 30 values, where each value is a distance table item. And do we just write it like this now? And each of these things is an array like this with extra bits is equal to like 0 and range start is equal to 0 or 1. Does this like compile? If I zig build, I think that it won't even try to compile that stuff because it's all unreferenced. So I have to try to use this thing. Okay, so say we want to write the value here. We want to write the value 17. Do we I guess we would do something like function distance code, and we're going to return I guess a code. This is a little sketchy, but we'll see. Because this guy is our like a Huffman code has a value and number of bits encoded in them, so that's kind of why I'm using this type. And here we're going to take in like value or distance, I guess, as a usize, u64. Max value is 32k, so u32 I think fits that. Python 2 to the power of 32. I'm pretty sure that. Yeah, that's way too big. 2 to the power of 16 also fits. So it could be like even an i16. Okay. So we'll say u16 for now. Fine, that's good enough. And what we're gonna do is we're gonna say for each distance in the distance table. So we have like some distance item. And for each of these, we're going to say, is the value within distance item range start plus 2 to the power of extra bits minus 1. Or I guess we don't have to subtract 1 because we can just say less than. So we'll say if the distance is less than this shit, then this is the table we're using, and we can just generate the code, right? So I guess here we need to start with the start code. And we say, we take the code, and then we read some amount of extra bits. And if we are reading least significant bit to most significant bit, then the extra bits are going to be shifted to the left and masked in. So this is going to be code start code, or this thing shifted left by 5. And then I don't know if we need to bit reverse the second half of it. I guess we should assume that we do. Because we had to bit reverse the first half, so why wouldn't we bit reverse the second half? So I guess what are we reversing here? It's like the range, subtract the range start. So distance, item, range, start. And then we shove in the extra val. And the number of bits, I guess. Okay. And then we have, like, return val is this, and num bits is equal to distance, item, extra bits. Jeez. I have absolutely no idea if this is right, by the way. But we can maybe write a test for it instead of just blindly assuming. So we can write a distance code generation test, and let's just see. We expect, let's just like put the value 4. Okay. I guess here we have to maybe error out if the code is not writable. We could either error and say, hey, what the fuck, you gave us an invalid distance code, or we could give an optional and say like, oh yeah, that's not a valid, we don't have that one. I think erroring out is probably more reasonable. And then we can just say like return error invalid distance code. And I guess we should log an error here. We could say like distance code is not valid. No, that's a useless fucking log. We'll just write this. Okay. So we get a code. We need to try now. If you don't try, you'll never succeed, you know? And so if we understand this correctly, we should get the value, sorry, we're not trying to get 4. If we were going to write 4, we would expect to get back the code 3. So we can try that. We can just say stood testing assert, no, expect equal. And I think it's expected then, what the fuck did I just do? I think it's expected value first. Yes. And then we can try getting a more advanced distance code, like the value maybe, let's try like 760. And if we understand this correctly, it should be 760 should be the value 18 for 5 bits plus 8 more bits. So it's going to be 760 minus 513 shifted left by 5. 7922. Ooh, that's actually not what we expect, because we expect a bit reverse. So let's do 760 minus 513. Let's look at that. And maybe format this as a Boolean. So we'll say like x equal this, and then say, hey, could you print x as a bool? Great. And this is how many bits? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to expect this to be 0b 1110 1111 because it's going backwards. 239. shift left by 5, add 18. And so this is what we expect. So 76666. And I guess we should we can just slap the Python code in here as, you know, some sort of pseudo documentation for what the fuck we've done here. Okay. We'll just say manually bit reverse. Okay. Zig build test. Code is not marked pub. Fine. Like, what do you want from me? I'll write pub. And I guess I probably have to write pub on these as well then. No? They just come for free? Oh, because pub's only for functions, not for fields. And then it's complaining that we didn't fill in our table well enough, which is true. We did not fill in our table well enough. He's such a whiner, this guy. So this is 1, 2, 3, 4. Then we have 5, 7, 9, and 5, 7 are 1 extra bit. 9 is 2 extra bits. Flashbang? Oh, don't worry, I'll get you a lot of times. Don't you worry. So it's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. 6, 6, 7, 7, 8, 8. It's just pairs of 2 over and over again. 7, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, 11, 11. How many of these do we get to? We get to 13. 12, 12, 13, 13. And you know what? I'm starting to think that I could have computed this. Now that I'm noticing that there's this extra bits pattern. But we're already committed to doing it the dumb fuck way. So, you know, what you gonna do? 17, 25, 33, 49, 65. $97, 128, 97, 129. I'm off by 1. God fucking damn it. 1, 3, 1, 2, 3. Fine. Fine. We'll fucking compute it because this copy pasting is more error prone and more confusing. What the fuck? Fine. Function. Generate distance table. And this is going to return 30 distance table items. We have some var. He's returned. And that is just same shit. Yeah, so it's 4 zeros and then everything else is pairs of 2. Yeah. Okay. All right. So 4 0-bit segments. 4 elements with 0 extra bits. All other then pairs of 2. And so we'll start with this var dist. Functions fine usually use labeled blocks for stuff like comp time table gen. Interesting. I could see the argument for that, I guess. I feel like I'd rather have the a named function, personally. Okay, so we start 1. And so then we go for I in 0 to 4. we discard the thing, and we say, I guess we take I, and we say ret I is equal to extra bits is 0, range start is equal to dist, and then dist plus equals 1. So that should be 1, 2, 3, 4. Great. For 0 to 2, we say we're gonna do something. I haven't really figured it out yet. I guess we'll just call this X because I don't want to name variables yet. And then, I guess we'll say var I equals 4. Maybe we'll even just start here. Var I equals 0. And we'll just use while loops, and I think that might make this kind of cleaner. So here we'll say while I is less than 4. We do it this way. And then we say while I is less than 30. I plus equals 1 in this inner loop. And here we're going to go for each of these. So our ret I is going to be extra bits is going to be I minus 4 divided by 2. Does that make sense? So no, I minus, so 6 minus 4 divided by 2 is 1. So no. 8 to 3, 10 to 4. So how do we get from 10 to 4? We subtract 2, then divide by 2. 4 minus 2 divided by 2 is 1. 5 minus 2 divided by 2 floored is 1. 6 minus 2 divided by 2 is 2. Yeah, so we do I minus 2 divided by 2. Okay. I think that makes sense. And then range start is dist, and that means we have to increment dist every time. So dist is going to be added by however much we could fit in that many bits. So if we're at 4, 2 to the power of 1 is 2, and we end up at 6. But I think we should end up at 5. We should start at 5 here. Yeah, so 5 to 7. Yeah. So dist plus equals 1 shift to the left by extra bits. There. Sure, maybe. Who fucking knows? Who knows? But I think that might do it. Zig, build, test. Let's just see what fucking happens. Expected, comma. Shut the fuck up. Like, you're such a whiner, you know? He always makes me do what he wants. What is even happening here? I actually have absolutely no idea what the fuck is going on. I must have just like forgot to close some bracket or something. These errors are starting in such a strange place. Expected expression found var. This isn't even aligned with a var. LSP restart. Hello? Oh. What the fuck is going on here? I must have just accidentally copy-pasted something, I guess? I don't know when the fuck that happened. That makes a lot of sense. Okay. Index is runtime known. Fine. I'm surprised that this is runtime. Why is this? Can I not loop with comp time values? Can I make like comp time function I want to like force this whole thing to run at compile time. Because I don't see any reason why it wouldn't be able to. But I guess I could also see a restriction where you need to have only constants, comp time block. Okay, so that's why Two-Step was saying that he usually does this in like, you do block is colon this thing, and then you write comp time here, like this, and then oh, just do comp time. But don't I have to return a thing? Oh, you do it inside the function. Ah, I like it. I like it. I like it. That's clever. Okay. But index value is runtime known. So this is at extra bits, struct requires blah, blah, blah. So he's probably lazily instantiating here. Index value is runtime known. Index value, index value. Oh, I guess I'll just write U64 here or something. I just want to get past it. Okay, shifted left by extra bit. So here we have int cast, I guess. Unable to cast runtime value to comp time int. What is it complaining about? Why is this shift? Oh, because this one is a comp time. So I need to like as U64 this one to get this thing to be able to be int cast. Probably. Unable to resolve comp time value. What? Note, argument to parameter with comp time only type must be comp time known. Is expect equal comp time? Oh, they're expect like the same value here or something. Yeah. So it's here I wrote code val. And here I need to write like as usize 3 or something, as U64 is what these guys are, I think. Error is ignored. Okay, that's a lot better. These error messages have to get better, man. I know I heard that somebody was saying that they do better in Zig 012, but they're pretty bad right now. Pretty hard to gauge. This int cast for this shift is truncating bits. That's not good. This is coming from distance code 4. Bit reverse extra file. Okay. Can we maybe GDB this thing? Run it. Backtrace. Frame 6. So we have val 0, numbits 0, which is garbage. So that makes sense that it's failing. It's not really a valid input. Okay, so we're in this function. Sorry, one sec. Okay, so we have distance table. We have some item. The extra val is the distance from the start of the range. And this distance from the start of the range is 0. Right, we got a bit of 0. I see. And I think... So here, distance is range start. Okay. So this can be 0. Extra val can be 0. That's no big deal. But extra bits not being 0 as well doesn't make sense. Right, so if extra bits is 0, then we have a fucking problem. I see. So we just need to special case. We can't do this if extra bits is 0. So what we'll do instead is, I guess we'll say const val is equal to if distance item extra bits is equal to 0. It's just start code. Else we have this shit. Val is equal to val. AFK for a few minutes, but I heard there were comp time issues. Yeah, and I don't even remember what they were. I think it was related to... Yeah, I might try closing a whole function body block in a comp time block. We did end up doing that. There was something else going on, though, that I don't really remember. I'm sure that we'll see it again later, though. Okay, that test is theoretically succeeding. Let's throw a little bug in there where we try to compare to something else. That fails. So we are chilling that at the very least, the distance code we got out of this is what we think it should be given our current understanding. That doesn't mean it's fucking right? We don't really know like if we're correct in our understanding or not. But at the very least, we got what we expected to get, which is a good sign. So here, we should now be able to just write, instead of doing this shit, we can say var distance code is equal to, let's try like 10. And I forget, is this a failable thing? It is, so we have to try here. And then we write bits, distance code val and distance code dot numbits. Cool. So in hello world, we have HELLO space WORL. Yeah, okay. So that that's a valid code for our string of hello world. And let's just see it. Sig build, and we run this. So here, real decompressor found hello world. So that's not good. We expected some amount of extra shit at the end. We expect 3 characters from somewhere. So let's start with distance code of 1. Here we get hello world with 3 Ds at the end. So that's great. We were copying that last D 3 times. And so let's get a little further up. Let's try 3. So now we should see hello world. He's still a D 3 times. That's not good. So maybe we should still debug print the distance code. Distance code. Because clearly there's something wrong there. So here we got distance code val to numbit 0. So our numbits field on here is just fucking bugged. Std log debug does the new line for you automatically. Yeah, but then it's a debug log. I just want to print. You know? Semantically, maybe very slightly different. So numbits is not extra bits, it's 5 plus extra bits. So now we got val2 numbits 5. And then we got hello world, but not with our trailing shit like we wanted. So let's go back here. Distance code 1. Let's try 1 again. Oh, do we have a hard-coded 5 star? No, we have numbits 5. So Real decompressor found hello world da 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 da. Great. Distance code 1. Hello world da 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 da. It's still the same shit. Which is a little concerning. Shouldn't this be like the fucking same? Like this distance code 1. Here we got val 0, numbits 5. Oh, hold on. Okay. So distance code 2. We have val 1, numbits 5, but no thing because we didn't bit reverse. The bit's not reversed. Why is it not reversed? Start code, bit reverse this. Oh, we just didn't bit reverse when we put the thing in. Or maybe we need to bit reverse here. I think that makes sense. So we have this table of values, and when we actually write them out, we need to bit reverse the thing. So this is 5 bits here. Yeah. And I guess we need the bit reverse here as well. So var val is equal to this bit reversed thing. Boom. If the extra bits is not equal to 0, then we adjust val a little bit. So we say val or equals this shit. And I think that's kind of like an okay, cleanish way of doing it. Okay, so now we're saying LDLDL again, which is good. We copied 3 bytes repeating from the L. So now it's like up the ante a little bit. We'll go back 3, and we should see the RLD twice, which we do, RLD. Great. And if we go back 4, now we should see ORL at the end. ORL, great. And now let's go back 10. And we should see ELL, HEL. So 10 might have, I'm either off by 1 or I counted wrong. So if this is 1 back, 2, 3, 4, 5, 6, 7, 8, 9, 10. I feel like there's an off by 1 in there. Oh, no, wait. So D is 1. So this is 1. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it feels like we're off by 1. So how could we end up off by 1 for value 10? I guess we just have to fucking look at the code. So we have val is 76, numbit 7. So it's numbit 7, extra bits 2. That makes sense. 5 plus 2 is 7. Great. And let's maybe take a look at what 76 looks like in binary. 1, 2, 3, 4, 5, 6, 7. And that's how many bits we expect. So we want to see the first 5 bits reversed. There's 0, 1, 1, 0, which is 6. So that's this distance code, which is, or the first code is 6. So that gives us 10 is in the range, not 12. Great. And then we reverse the last 2 bits, which is 1. Which does seem like the right code to me. If this starts at 9 with an extra bits where it would be 0, then incrementing 1 there should get us from 9 to 10. I feel like I'm missing something. Okay, let's go back to 2. So if 2, we should see LDL. And can we just keep going up by 1 and seeing, maybe I don't think I'm miscounting. So we can see where it stops being consistent. So we have RLD now. Incrementing 1 more should give us to O. So it should go ORL. Great. Incrementing 1 more should give us starting at W. Is this a good way of debugging? Just adding 1 over and over again? WORL. Okay. 1 more. Should give us space WO. Space WO. Great. 7. Should give us O space W, 8, LO space, great, 9, LLO, 10, ELL. Yes, I'm just an idiot. I just can't count. I was just off by 1. I thought we were off by 1. We're not. It's just working correctly. Great. Cool. Okay. So generate test block and decode with real zlib. I guess we have generated a block that has variable extra distance, but we should also give the same treatment to the length table, I guess. So at some point we did like generate distance table, and now I guess we are at 155, and we are looking at generating the length table. Okay. So generate, I guess this should go down here. Generate length table. Okay. So this has 285 minus 257. Oops. Okay, calc. 286 minus 257. 29 elements. 29 elements. Where were we here? And I guess distance table item is still a fine, like, extra bits and range start is what we need. Maybe the name distance table item is a little bit confusing, so we're just going to put a fix me on here. This is valid for the length table as well. Maybe we'll call it like LZ77 table item or something. And this is 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 0. Okay. So this is probably going to be similar to this guy. He's going to start at 3, though. We have 8 elements with 0 extra bits, then chunks of 4. So we start with distance 3, we make our way up to 10. So while I is less than 8, I guess. Then we say while I is less than 29, we go from 0 to 4. Yep, and here we just have to do an extra check here because it's not a multiple. So we say if I is greater than or equal to 29, break. There we go. There we go. And so this math is going to be different too. This extra bits is no longer 1 minus 2 over 2, minus 2 over 2. So here we're going to have like 8 goes to 1. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to 2. So minus 4 over 4, I think. So 8 minus 4 over 4 is 1. 12 minus 4 over 4 is 2. 16 minus 4 over 4 is 3. Yeah, that's fine. That is the correct mapping. Dist plus equals, it's no longer 2 to the power of extra bits, I don't think. It is 2 to the power of extra bits. So we have like 2 extra bits, we add 4 to the distance. Cool. Yeah, okay. So we can now generate a length table. Okay. And the question is this extraction code the same for distances and lengths? We look up the code, we read the extra bits, and we OR those in. Okay. But the problem is with this distance code thing, we are kind of fixed at 5 bits for the initial thing. And I don't think that is true here. Here, it's more like we Huffman code this value. So we do 257 is like the minimum value, 285 is the highest. 257 to 285 is like Huffman coded. So I think that the output here doesn't make sense, actually. And actually having this as a Huffman code for the length thing also doesn't make sense. We have to export 2 things. One is like the Huffman coded index, and then the extra bits separately. Yes, that makes sense. I suggest having a lookup table instead of calculating the extra bits. I think that copy-pasting this table versus calculating ends up being more error-prone. I think. Because if I copy-paste the table, in order to be sure that I'm correct, I have to unit test every single possible value. Like, not every possible value, but all of the values, for each set of extra bits. It would be an array of ints. Is that true? A lookup table of what? A lookup table that goes from code to start value? No. I think I'm missing something because I don't see a way to avoid code to extra bits. But then I still need to store the distance value, like the offset, the starting value as well, right? I do have an array that's going from code to extra bits. My array is going from code to extra bits plus range start, right? So like 6 goes to 2.9, 7 goes to 2.13. Am I high for thinking that that's a reasonable thing to store? And then like that's in a lookup table that I'm using later. It's just I'm generating the lookup table with math. Because that way I have a better confidence that all values in the table are reasonable. Does that make sense? Like, is that a reasonable... I guess I don't think I'm really asking you. Comp time? Yeah, it's in a comp time block. I think I'm saying that, and I'm saying it like a question because there's an opportunity for you to tell me, no, this doesn't make sense for a really good reason. But unless you give me like a good reason that convinces me, I think I'm just gonna stay with what I think is right. Because I do think that this is easier for me to have confidence in after testing a few iterations. Okay. So here we want to get the length code. Not just optimization. I see. But optimization-wise, it's all being generated at compile time anyways. Who fucking cares? I think. Okay. So given some length value, which can be in the range of 0 to 258. So I guess we're going to use Z16. We want to get out some sort of like length code. Random question, why dark mode text editor but light mode desktop and browser? Light mode desktop because it was the default. Light mode browser because it was the default. Dark mode text editor because it was the default. I guess my color scheme technically isn't default, but the terminal is dark by default, and so I just picked a theme that kind of like fit with the terminal itself. The real reason is just like I don't really care. And so it's just like whatever happens, happens. What is this guy gonna have? I can respect that. Yeah, can you expect this like the constant flashbanging though? People do get unhappy about that for some reason. They're like, ow, my eyes. And it's just like, I don't know, man, just close them. What do you want from me? It's like, you want me to be reasonable. Well, get fucked, I guess? Okay, so my length code, he's going to have the Huffman coded part, which is just going to be a number between 256 or 257 and 285. Then he's going to have an extra val, which is a Huffman code, i.e. something that has a number of bits associated with them, a value with some bits tied to it. Like, so he's going to be like, you write the value 265, and then you write one extra bit. Yeah, I think that's reasonable. So the idea of moving through the table, we're going to look through the table, and we're going to have a length item as well as the start code, start length, I guess we'll call it. No. This index is going to be an offset from 257, I guess. So what do we call that? We'll call that code offset, I guess. That's a reasonable name. And we're going to say, hey, if our length item range start is greater than or equal to the length that I'm trying to use, why is this different than this? Distance is less than the range start plus 1 shifted by extra bits. Oh yeah, that is the same thing, huh? Okay, yeah. So if my length is less than length item range start plus 2 to the power of length item extra bits. And then the bullshit comes from having to cast this to a U8 or something. Yeah. Okay. So now I have like the appropriate section. The Huffman coded value is going to be 257 plus the code offset. Yep. And extra val is going to be some Huffman code that has a value associated with him and some num bits. So num bits should be easy. This should just be the length item num or extra bits. Nice. And then the val is, I think we have to do the bit reverse bullshit here. So I think it's just the val is equal to the bit reversed length item extra range start. No. Extra val is the distance. Yeah. So we have the offset from the range start. And we then do a bit reverse of extra val and that. No shift 5 in this version. There's no fixed 5-bit section. And we'll call this offset, I guess. And this would be length item. And then we can just return length code. So the Huffman coded section is equal to Huffman coded, and the extra val is equal to this extra val. Okay. And I guess there's no reason for us just to not do this inline. Like this, and like this. Boom, 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 boom. Dun, 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 dun. Okay. There we go. I think that's right. We can do a quick little length code generation test. So let's start with length code of 4 should give us code 258. So what does my length code type look like? I forgot already. Huffman coded and extra val. So my Huffman coded should be 258. And extra val, I guess, should have a val of 0. And num bits should be 0. I guess I don't really care about the value if extra bits is 0. It doesn't fucking matter. Okay, and let's try something more advanced. So let's try something at like maybe like let's try like I don't know 700. So I guess we rip out Python again to calculate this. So we have 700 minus 513 is the offset. This is 187. We want to print this as Boolean. Okay, and so then we have 7 bits. So this is 1, 2, 3, 4, 5, 6, 7. That's more than 7 bits. Am I high? Oh, it's 8. That's why. Okay, so then we have 110, 11101. Boolean, so 221. So let's copy paste that a little bit one more time just to have something that we can write as a comment here. Which means manually reversed. There we go. So our Huffman coded value should be 18. Sorry, not... Oh, fuck, I was on the wrong table. God damn it, I was looking at the wrong one. Let's do the value of 140. Let's do 140. Okay, so we do the same shit. It's 140 minus whatever range of that start is. It's 131. And then we manually reverse it, which is 1001. But there's a 0 at the end because it's 5 bits, I think. 5 bits. So we should get 18. So we should copy paste this into here. Yep, and then here we write down, this is manually reversing 5 bits. Yep, so we should see 18 here, and we should see 281 as our Huffman coded value. Zig build test. He doesn't like this. Expected U6, found U64, so we need to incast there at 201. Okay, expected U16, found usize. Okay, so code offset, we just incast this, I guess. So that it fits into U16, bada bing, bada boom. We have to return an error here. Okay. And now, index out of bounds. Interesting. What test is this in? This is in static Huffman block decompression. Am I high? We haven't changed that at all, right? Oh, we have. We have. Okay, can we run a test filter? Zig test with the test filter. Test dot. Is this in zlib.zig? I think it is. Length code generation. This is all I want. Okay. Integer cast truncated bits at line 8. So this is probably the same shit where I forgot to special case the 0. Where it was 0-bit case. Yep, numbits is 0. Special case there, so we just say if So we have to do a similar trick here. So we say extra val is equal to 0, and then if length item extra bits is greater than 0, then we are allowed to do this bit reverse. Okay, and then here we can say val is val. Okay. Test filter is substring search, so leading tests isn't necessary. Good to know, good to know. Good to know. Okay. Expected equal found. Okay, so does it really not tell me? It doesn't tell me what the value was? What a silly thing. So this is at 526. That's here. What did we get instead? Stood, debug, print. What the fuck is our code? What is it? It is 273. Oh, it does say expected 281 got found 273. I just can't fucking read. Okay. So let's look at this. Length code 140. 140 is definitely in the 281 range. So why is it giving me 273? That's way the fuck back here. And it must just be because my table generation is just bugged. Right? I must have just done something wrong. So can we just print the length table? Just to see? Invalid format string, length table, I'm an idiot. This should say any here, and the length table goes here. Let's just take a little peek skis. How bad is it, you know? So here we have range start 3, 4, 5, 6, 7, all with extra bit 0. 8, 9, 10. So we get 0 to 10. Or 3 to 10, I should say. 3 to 10 are all looking good. Then we should have 265. So we should have start at 11, 13, 15, 17 with extra bits 1. So we have 11, 1, 13, 1, 15, 1, 17, 1. Okay, seems fine. Then we have 19, 2, 23, 2, 27, 2, 31, 2. 19, 2, 23, 2, 27, 2, 31, 2. Okay, I don't see the problem there. 35, 3, 43, 3, 51. 35, 43, 51. Yeah, so what the fuck is the problem? So I think that the table looks okay. It's more likely, I guess, at this point, this. So if length is less than this, it's because this sign is fucking backwards. How come it worked on distance? Oh, because I was just testing something else. So if length... Oh, no, yeah. If length is less than the range start plus 1 to the power of extra bits, I don't see the problem here. Maybe what we should do is we should stood debug print. Or maybe we'll just fucking GDB here. I am missing something. P length. Source file is more recently executable. Fine. Zig test. We'll fucking compile again if you fucking want me to. Like, what do you want from me? P length. So the length is 4. Not this one. P length. It's still 4. Okay. We have length. P length item. So we have extra bits, range start. Okay. P length. P length. Oh, is there some fucking... Is there some fucking like bracket shit that I fucked up? Because you have length, item, range, start, 4. Yeah, I'm gonna put some brackets in here and just see if it fixes it. So this is, we want 1 shifted left as like 1 unit of thing. And let's see if that fixes the test. Expected 18, found 5. I think that did get us farther, because that made it to here. That passed this now, and now we're bugging out here. So this is found 5. Oh, because num bits is 5. Oops. And the val is 18. I was just testing the wrong thing. Testing the wrong thing. There we go. Okay. That's passing now. Great. Great. So, we can generate a length code now, which means that here, instead of writing this 257 by hand, we should be able to say var const length code is equal to length code, and let's say that we want to go back let's say we want to copy something really big. We could do something like as big as 24 bytes. Here, we would write out length code Huffman value, or Huffman code, maybe? I can't remember what we called it. This is try. And so now we should be able to autocomplete here as Huffman coded. And then we should be able to write the number of extra bits. So Huffman write bits. We should be able to shove in length code extra val length code extra val num bits. Okay. And now if we say zig build and we do this, we run hello world, we decoded, we found hello world once, twice, plus 3. So hello world is 1, 2, 3. I guess we should fucking echo dash n this wc dash b c 11. So this was 11 times 2, 22, plus 3 is 25. So what did we punch in? 25? We punched in 24. So I'm probably either let's just do this one more time and just see if we go from 25 to 28. We went from HEL to plus 1, 2, 3, 4 more. 24 to 28 plus 4 more. Looks like, I'm pretty sure it's right. Pretty sure it's right. What is my color scheme? It is Sonic-Eye in NeoVim, but with term GUI colors turned off, plus the default Alacrity color scheme, which is a little bit of a combo. A little bit of a combo. But it looks okay. Okay. Sonic-Eye? Yeah, like it's Sonic-Eye MM. Just some package. I don't know. I think that this is supposed to be like a copy of the Visual Studio Code color scheme, maybe? I can't remember. Thanks. No problem. Okay. So now we have this like length and distance code thing that is correctly being interpreted by zlib itself. So now we can actually try decoding it ourselves in our version of our decompressor. So we're not keeping track of any previous output thing right now, but I think maybe what we should do is we can start by just decoding the values and printing them out. And if we get the values that we expect, then we can start trying to copy them from where they came from. So we can say else in this block, we have a value and it's greater than 256, which means that we have to start decoding the length value. So I guess we look at our length table and we just jump in val minus 257 bytes. So we say const length table index is equal to this. And then we have to check that we're within range. So if length table IDX is greater than length table len or equal to, we error length code invalid. Then we can just hard index in here. And here we have something that gets it here. So const length code is equal to this. I don't know if it's a good practice in Zig for me to put ampersands here to be like, yeah, I mean, I don't want to copy this thing out. I don't know if like that should be my default or not. Or if I should just be defaulting to copying and letting the compiler optimize away. I guess they're like optimization wise, the compiler either might be able to more easily prove that there's no shenanigans going on here where it might have to like update pointer reads. I don't know. It doesn't matter. Because like here it might be able to say, okay, I'll copy this shit into registers and then not worry about it anymore. Where if I put an ampersand, maybe it has to worry about like the pointer data changing under the hood and has to reload every time I access it. I don't know. So maybe the answer is doesn't fucking matter and I'll just do this. So my length table has a bunch of distance table items in it. So here I have extra bits and range start. So here I can just say, hey, I would like to read extra bits, more bits. So this is reader, self-reader. Inside, this is a bit reader. Yeah, this is a bit reader. So I want to read bits. And I want to read some amount of them. This many of them, even. He's going to tell me how many I got. Bits consumed, we'll call it. And we'll try. Should I learn Zig before Z if I don't actually give a shit about C? Let me think about that. I think, so when people ask this question about Rust, I say fuck no. I say when you're learning Rust, fucking learn C first. Zig, though, the language itself is pretty decent. But documentation around the language, not so great. Because it's kind of like an in-progress, in-flight thing. So, in my opinion, you need some amount of like ability to dig in order to use Zig effectively. That's how I feel. I mean, but I could be wrong there. But my gut says that it would be hard to learn Zig without fundamentals. Just because you can't Google, like, how do I do X in Zig? That's like a hard thing to do, and because like there's just not enough resources. And so what I find myself doing is I Google something, I can't find it, I chat GPT it to see if like maybe he's synthesized something that I don't understand. He's always wrong. He just says lies every single time I've ever tried. And then I dig through the standard library and code and then find what I want. That's been my experience. But I do understand that like my way of learning isn't necessarily the only way of learning. So I would recommend learning C first and getting good at like navigating code and stuff. But like if you like, it depends on what you mean by learning C. If you're like new programmer, I would say C. If you're like someone who's done a lot of coding and they just haven't learned like a low level language, then like Zig's probably fine, would be my guess. But also you're like kind of like tying yourself, you're like, what's it called when you something to a horse? Tie yourself to a horse. Is that the phrase? No. There's like some phrase that's like, is it betting on a horse? You're betting on a horse that like is not guaranteed to like turn out, right? Like we don't know in 4 years if anybody's going to be using Zig. We do know that for as long as like code exists, we're going to be using C. C's not going anywhere for like forever, right? So when you're like, should I learn blank? It's like, well, it really depends on your goals. It really depends on like, yeah, I guess just what you want and what you have experienced. So I would recommend C, personally. But I can see the argument for wanting to learn Zig as well. So kind of like a lot of words to say, I don't know. Okay. So here, if bits consumed is not equal to the amount of bits that we wanted, that's an error. Error, stream ended or something. Not enough space, invalid data. We'll say invalid data. And then here we have to bit reverse the thing. So here we want to bit reverse. Here we need to say what we want out. So here we want out a U64, I guess. U16. We'll call this extra. Extra val, I guess we'll call it. We can reverse the extra val, expecting it to be this many bits. Slump. And okay, then we just add that to the offset. So var length is equal to the length code range start plus the bit reverse thing of this. If you want to learn Zig, I'd recommend joining one of the communities. Yeah, that is something that I didn't do. I haven't really been on anywhere where people can ask me for help other than people that happen to have found my Twitch stream. So that could definitely help as well if you have people who are willing to like help you through questions. There's a lot of languages in the C replacement space, Zig, Odin, V, Carbon, it's kind of dizzying. I would not bet on any of them. That, like, I could be wrong, but I think that there's no guarantee that any of them work out. Rust is great, but didn't teach me about pointers. Rust, I think, is great for kind of like forcing you to think in a way where you won't write bugs, which is great. Like but it's very fucking hard to pick up. I'm surprised if you learned Rust before C that that's like something that you were able to do. Because to me, it seems like you like without like a fucking strong understanding of like where your memory is, I don't know how you would do it. And I'm like, yeah, it's impressive, I guess. Okay, so now we need to parse the distance code. I returned pointers to locals all over the place when I started Zig. Dude, I haven't been like, I've been out of practice with like C++ and C for a while. I haven't really written them a lot for like maybe over like around a year or maybe more. And I've been writing a lot of Rust, and the amount of times that I've invalidated references by like reallocating a vector or something while holding a pointer, or like deleting stuff while I'm iterating, or like returning a pointer to something that I allocated on the stack, or something that I accidentally de-inited. Like I've forgotten that I have to handle, like, be careful about that. So it's good to get back in the habit, but man, there's something about like when you write Rust and it just works, right? It compiles and it just fucking works. Where like in Zig, I'm back in the like, okay, we're cracking out GDB, we're looking at all the bugs that I wrote. But, you know, then you can just say, well, fucking get good, you know? Okay, so let's try to read some distance stuff out of here. So here we need to read 5 bits fixed. Distance start distance. I guess we'll make this a val. val distance equal to self reader read bits U16, I think. And we're going to read 5 bits, and we're going to write this into bits consumed. We're going to say if bits consumed is not equal to 5, there's a fucking problem. And maybe we even put a little log here. Distance code was not complete. And then that means up here we should say length code was not complete. Writing val distance is not good. Var distance, much better. Va : distance, no good. Okay. So now our distance code, we need to read our extra bits. So we look up in the table. So we say distance table. So here we can say if our, I guess this is a distance code. We'd say distance code is greater than distance table.len, I guess greater than or equal to. If this is that, then we are erroring out. We cannot index. Now when I look at Rust code, it looks very noisy. Definitely like anything generic in Rust is quite noisy and a pain in the ass. There's a lot, but I don't know. I feel like it's like a taste thing, I guess. Yeah, I don't know. It doesn't feel too bad to me still. We can std log error and say distance code was too big. Return error, invalid data. Let's just return error, invalid data everywhere. I do miss the chains. Yeah. Okay, so now we look up in their distance table. We look up our code. Yep. And what comes out of this thing? Our distance table has distance table item, so extra bits and range start. So it's just going to look a lot like this. Yep, bits consumed. We'll say here distance code was not complete, and here we have var distance is equal to distance code range start plus bit reverse of the extra val. Yep, I think that's fine. We'll call this distance index here so that we can use it like this. Boom, 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 boom. Okay. And then we can std format debug. No, std debug print and say found length this and distance this. Length distance. Okay. And if everything went according to plan, when we run this, we should see our distance and length values that we put in our static block by hand. If we did it right, which we might not have, but we might have. Bits consumed. What's it bitching about here? What's it complaining about? Variable of type comp time int. I see. So this needs to be a usize. Fucking whiner. And then I missed argument in 411. There we go. And this guy is, I forgot to write try somewhere, I guess. Probably right here. Try. All right. So, found length 28 and distance 66. And the question is, are those the values I wrote? I don't think they are. Length 28 is good, but distance was supposed to be 10. So length 28, good. Distance 66, bad. So what's going on here? I guess we just bust out GDB. Break here, run. Really? Oh, run input data hello world. Okay. And let's just list. What do I like? I don't know what I expect to see here. I just want to like look. So print distance IDX 12. So if I wrote the distance code 10, the fact that I'm getting a 12 here feels fucking wrong to me. And it's because we forgot to bit reverse the fucking distance. Pretty fucking sure. Pretty sure. Distance IDX is equal to bit reverse distance IDX with 5 bits. Quit, zig, build, and run it. Much better. Cool. So we have decoded our back reference, and the last thing to do is just fucking use it. So I think what we just do here is we have this like previous what is it? Previous data, I don't know. And this is supposed to be a stood ring buffer full of U8s. Is this ring buffer a type like that? I assume it is. Oh, maybe not. Oh, it's kind of hard-coded to U8s. That's interesting. I would have expected their ring buffer to be a generic type. But that's okay, because we happen to be okay with U8s. Stood ring buffer. And here we say that our previous data is a... I guess I should need to read some docs here. So, is this thing, when I push to the ring buffer, what the fuck happens? There's data, read index, write index. I can write to the ring buffer, returns error full if the buffer is full. Can I write linear FIFO is another ring buffer, which is generic. Interesting. Zig standard library. Standard library. So we have linear FIFO. With a buffer type. So I can say, hey, I have a static size. Buffers passes slice to the initializer, or it's dynamically allocated using my allocator. Oh, interesting. Okay. And I have the ability to write data, allocates more memory as necessary. So this won't do like an automatic overwrite, I guess. Write a single item to the FIFO. So why is write different than write item? I guess the write item probably also will reallocate, would be my guess. Write, ensure unused capacity 1. Yeah, okay. So I have my options are to use a ring buffer, and if it says, hey, I'm full, fuck off. Oh, I guess maybe ensure capacity might fail if I have a static buffer size. That seems likely. So if it's greater, we can try to ensure total capacity, and if the buffer type is not dynamic, then we will, if it's dynamic, we resize, else we just say, oh, fuck it, I give up. Except if it's static, it has to be a power of 2. Okay, so here, if I were to use the ring buffer, I have to manage like the overwriting myself, but same with ring buffer. I guess ring buffer probably matches what I want better. I think it does. So I'm just going to use ring buffer, but it's good to know that linear FIFO exists. Okay. So previous data, we're just going to say stood ring buffer init with an allocator and a capacity. Oh, it's kind of interesting that data is a slice here. So they don't actually use like an array buffer. They just allocate the slice, just pray to God. Okay, sure, but it doesn't really matter. So this is 32K, I think is the size I'm supposed to be using? Is that right? 32,768 divided by 2, divided by 2, divided by 2. Like, is that whole number? Yeah, it is. Yeah, okay. And so now every time I read some data, I have to pop data out of the cache so that I can write however much I want to write. Which means I want to... So if I consume a byte from the ring buffer, that's not really what I want. I want to just, like, move the pointer. Ring buffer. Let's see. What's his API give me? What's he give me? So 0, 0 means empty here. What is their, like, full? There is full is if mask 2 right index plus self data length is equal to read index. I see. Modulo twice the length of the backing slice. Modulo this length. Okay, that makes sense. I think that's useful. Okay, so if I want to just say, like, fuck off, I want my read index to go down now, man. I take the read index. Okay, I'm going to be writing at right index. That makes sense to me. If I want to ensure room, so we can say, like, maybe function, ensure capacity. We have a ring buffer, which is a pointer to stood ring buffer. And we have some capacity we want to write. I guess this isn't what we want to do. Maybe it is. Sure, we'll do it this way. So all we should really have to do is move the read index. Right? That's all we have to do here. And the question is how much? So we want to see, I think all we have to do is we have to look at the capacity. So is there a capacity function on here? Returns the length. That's pretty fucking close. So we can say, wait, hold on, let's look at it again. The length function returns the length, which is adjusted right index minus read index. Okay, so we have ring buffer len. And we need the capacity to be greater than the capacity of the ring buffer minus the length. And so that's data, read ring buffer, data, len, minus this is the current capacity. Right? Simple. Now, now I want the capacity to be bigger, man. So if current capacity is greater than capacity, return. Nothing to do. But say it's not. Then what? Then I either have to increment or decrement the right read index. So when I write, I'm assuming that I increment right index plus 1. Uh-huh. And then I just have to increment my read index to catch up. So here I just have to say ring buffer read index plus equals current capacity minus capacity. No, other way around. Capacity minus current capacity. Yeah. Yeah. That makes sense. And then I probably have to do some bullshit like mask. I have to make sure that I match what they do when they increase the write. It's weird that they don't have any like reader. Consume a byte from the ring buffer and return it. Yeah, so read index is this. Okay, there we go. I think this should do it. Because it's mod 2 times, so at any point, as long as capacity is small enough, then this should work out. Yeah, I'm pretty sure this is gonna be fine. Capacity minus current capacity. I really do think that's it. And this is not B self, this is ring buffer. It is masked to a public function. Yes, it is. Great. And this should be ring buffer here. Okay. That all makes sense. So now when I read a block, I need to so here I'm reading a bunch of bytes. I need to put them into the previous section. So here first I'm going to ensure the capacity. I guess here I should assert that capacity is less than the ring buffer data len, or equal to. Otherwise, I need to do some sort of like have to chunk only write the. It's invalid to try to write too much here. And then all we'd have to do is like clamp this stuff. So yeah, it's fine. It's fine. But for now, we're not going to handle that. And we can just say self previous data write slice. Assume capacity. Output 0 to len. Yeah. Cool. And then down here, it's the same shit. So we have output at this index is this. So we just say ensure capacity ring self previous data. We assure that can write one thing to it. And then we self previous data write val. Yeah, like this. Boom. Boom, boom, boom. And this probably has to be try. This probably has to be error. Actually, I guess not. Does write have to be try? Write assume capacity is fine. Because we have assumed, we have ensured capacity ourselves. And we're going to corrupt data, but that's okay. We don't give a fuck. And that's all the places where we can write out data. So that means that we have all the data that we need. And we should just be able to read that stuff from the previous data. So does the ring buffer give me any nice reading utilities? Returns a slice for the region of the ring buffer starting at this with specified length. Start unmasked. Yeah, okay, so we just say, hey, give me this much shit from the given read index. But if I want to read from the end, that's not what I want. I want to read from like self previous data dot write index minus distance. Yes. So let's start by just printing out std debug print data to copy is going to be some string at this distance back. Yeah, let's do that. So self previous data slice at this. And let's pull out length bytes. Data to copy. Copy data is this. Yeah. Yeah, let's see what that looks like. We need to write some tries, catch some errors. You know how it goes. Ring buffer slice doesn't give us a nice little thing. So, right, because it comes in 2 chunks. So we have to do copy data first and copy data second. Like this. And data to copy, LO world. That's a really good sign. Really good sign. So there's a problem here where probably our distance is, or our length is too long. So we have to do something like const data or like input length is going to be copy data first dot len plus copy data second dot len. And we have to do like var. We have to like copy in chunks. So there's some loop while something. We do we copy the first part of the data. We push that to the output. Output, so we do like mem copy output from output IDX onwards from this. And then we copy the second half. And then output IDX plus equals copy data second len here, copy data first len here. Yep. And then we also have to copy this to our like reference buffer. So we have self. Oh, but that's kind of sketchy. I'll figure that out in a second. Fix me, adjust previous view. And what is our like exit condition here? We have like var output IDX start is equal to output IDX. And we'll say while output IDX start, while this is less than the length that we're trying to copy. Sure. Then we increment this guy, blah, blah, blah. And for each of these, we have to maybe limit ourselves to copying only the amount that we want. So we say const copy var copy end is going to be the output index plus length, but the minimum of that and copy data first length. output index is equal to copy end. And we do the same thing here, but with second. Yup. Yup. Sure. Yeah, I think that makes sense. So if we zig build now, does our custom decompressor give the right thing? Unused local contact? Okay. Surprising, but I guess we don't need it. So now our real decompressor found hello world, hello world, hello world, hello. And mem copy arguments have non-equal lengths. Fuck me. So this has to go to copy end. And I guess we should call this var copy len is equal to copy n minus output idx. This has to go 0 copy len like this. We do that again down here. Okay. Boom. So now we're getting integer overflow, copy end minus output index. That's surprising, because this should actually be copy end is the minimum of length, or first copy blah 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 blah. And I guess it's actually var remaining length. We need to adjust this. Remaining length like this. This is copy len. Remaining length minus equals copy len while remaining length is greater than 0. Var copy end is equal to output, or output index plus equals copy len here. Yep. That looks a little bit better to me. Okay. I think that's right. I haven't really thought very hard, but I'm pretty sure this is right. Would it be simpler to double slice, i.e. slice idx dot dot... What the fuck? What is that syntax? So you're saying I can type something like slice idx dot dot 0 dot dot len. What the fuck is that? This would be like a two-dimensional slice, which I don't think I have anywhere. I have two slices. I must be misunderstanding something, because I don't know what the hell that would even do here. Okay, we do the same thing again down here. Re-slice. Oh, I see what you're saying. Interesting. So here, I start at the index, and then I link it to the length. Oh, that's pretty cool. Maybe that would be easier. But I'm already committed. I don't think it's like easier enough for me to change anything. You know? Okay. And then here, yeah, I think we're chilling. So here, custom decompressor found hello world, LO world. That's really good. So we've managed to at least get one reference, and now the problem is that we're not looping the way we should. Because the real decompressor found hello world, hello world, hello world, hello. And so with this loop, I would have expected us to get the same thing. I would have. So why is that not happening? Oh, probably because I wonder if our output buffer is too short. So we could look at our demo Huffman compression, demo custom decompressor. Here we go. Our output is 4096 long, so that should be fine. Oh, that's for the real decompressor. Probably after the real decompressor runs, I run Rs. I read a block. Oh, no, that seems fine. That's fine. So I guess we should print, maybe we copy this line, run with GDB, break here, run with input data hello world, and print remaining length. So our remaining length is we expect to get 28. And we go boom, 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 boom. Boom, 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 boom. And we say print remaining length. And it's 0. So I feel like I missed something where... Can we run it again? So here, what is my copy len? 28. Surprising. P copy data first len. 28. There should not be 28 bytes in that copy data. P remaining length. Yeah, there's something wrong there. This copy data first lang. What the fuck is this? P copy data first. This is hello world, which should only be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes. So where's this 28 fucking coming from? Second should be empty, right? Second, yeah. Second is nothing. So we only have 1/2 of the buffer. And it's just, what the fuck is this 28? It's very strange. Uh... 28 is a very, very strange value for that. Like, super fucking strange. Oopsies. Fuck. So we were at line 454. So B zlib zig 454. No, quit. Fuck me. Yoinkies. Break GDB, break on this, run, help with input data of hello world. And like, what the fuck is going on in this thing? So he has read index, write index 11. That seems like super reasonable to me, right? So I've written 11 bytes, hello world. And when I call slice at, it's just doing some like weird ass shit. Like, what the fuck? Let me see. So when I get this slice at, oh, I ask it for a specific length. Oh, and it doesn't validate it. So I need to truncate. Oh, that's fucked. So I need to truncate to here. So I'm saying, hey, I guess distance. I want the minimum of distance and length here. Yeah. So if my distance is, if my length is smaller, then I copy the whole length at once. But if my distance is smaller, I need to batch my copies. Yes. And so now we get, hell yeah, baby. Look at that shit. Let's go. So here we said, hey, we have the string hello world, and I want you to go 10 bytes back, and I want you to copy 28 bytes from there. And so then we say, okay, well, we're going to run out of text to copy, so we're just going to copy the first 10 bytes here. And we're going to do that 2.5 times. Boom, and look at that, we get the same fucking shit. So the real decompressor, using real zlib, got hello world. We are on hello world, so we're 1 off here. I guess our distance needs to be +1. I guess. Hello world. Wait, hello world. So the real decompressor got hello world, then hello world again, and hello W. We got hello world. Hello? So there's a bug here for our length 28, distance 11. Let's go back in. Go hold. So they went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And they copied whatever this length is. 30? Oh, that's weird. It could be that it's copying too much on purpose, and then, like, because it's erroring out, that's not supposed to happen. Because, like, we wrote distance code, length code 28. So, assuming that we wrote the right thing, this is more correct, what we got. And, no, the real decompressor shouldn't be airing out anywhere that's relevant. Am I high? Okay. Echo-n. This thing. Now, count characters, 11. And then 11 plus 28 should be whatever we get here. 40. That's not 11 plus 28. So, our length code generation is fucking busted? It's interesting because our decompressor is consistent with what we wrote, which makes sense. So it just means that our tables are probably not right. Oh, that's annoying. That's annoying. So can we print out, when we generate these things, what our length and distance codes are? Generate length table. So whenever we say, like, length, is there an implicit +1? There could be. Let's just, here, print out the length code. And, like, just really look at it closely. So, length code, we got 271 with 2 extra bits. So, that's 271. 2 extra bits, value of 2. So, the real decompressor is giving us something that is 40 from 11. So they're giving us 29, which is a valid thing in here. It could be that we aren't supposed to bit reverse. Most significant bit first, e.g. bits 1110 represent the value 14. It'd be interesting to see if we get what we expect if we don't bit reverse in here. Is there implicit +1 because backward by 1 be the current character? For distance, I could see that, but for length, there's something wrong there, I think. Oh, I could see it, though. No, because you could say that the length starts at 3, so there's no 0 to worry about there. I think it's more likely that this bit reverse is wrong. So, can I just do val equals offset? Here, comment this out. Just to see. Just to see. So here, that ended up giving, gave us more here? Well, let's see. Oh, that's custom decompressor. Real decompressor now found this. Echo this WC and with no new line WC-C like this. Ah, okay. So the bit reverse is wrong because we can see he's getting, by bit reversing we got less stuff, which is what we expected. This is now going hello, 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 which means that in our custom decompressor, when we decode the length, we just don't bit reverse here as well. And now I think that we should be getting the same thing. So the custom and real version, this gives us hello world, hello world, hello world, hello. And we get hello world, hello world, hello world. Okay, so now we're off by 1. So our distance code, we need to +1 on it. Or there's a bit reverse bug in there as well. But for now, let's say we +1 our distance code just to see if that makes them the same. Hello world, hello world, hello world, hello. Hello world, hello world, hello world, hello. That's really good. That's really good. So that means that we're now fucking decoding the exact same thing as the custom or the real decompressor. And now let's just try adjusting this a little bit. We'll change it from 10 to 11. Oh, 11's invalid. We'll change it from 10 to 8 and see if we still get the same thing. So here we got hello world, hello world, hello world, we got hello world, hello world, hello world, hello. And we got hello world, low world, low. Okay. So I think it's a bit reverse bug again, not a +1. So let's go back here. And I don't know why, when we were testing this before, were we seeing, like, did we think that we had to bit reverse? Oh, maybe we have to bit reverse the first part, but not the second part? That would be so fucked. What seems possible. Okay, let's first git add-u, git commit-m, checkpoint. I just don't want to get lost. So the theory is that this bit reversal doesn't fucking have to happen. That's the theory. But this first half does need a bit reversal. This is what I think maybe has to happen. So let's zig, build, and see if we still get the same shit. So now we get hello world, hello world, hello world, hello world. Hello world, hello world, hello world, hello world. That's a really good sign. So these are exactly the same. We're consistent. And now let's change the distance code from 10 to 8 and see if we get the same shit. So we should be seeing low world, hello world, low world, low world, the world, hello world, low world. Boom, baby! Let's fucking go! Hell yeah. Okay, so that's really fucked. Look at this fucking generation code for the distance code. We generate half a value, fucking reverse the bits on it, and then or in more of the value, not bit reversed. What in the actual fuck is that? Like, what the fuck, man? Jesus fucking Christ. Okay. This is like the type of shit where it's like, this is kind of why it's fun to go through the full exercise, right? You look at this stuff and you go, oh, I read the spec and I get it. And then you fucking try to implement it and you don't fucking get it. And it's like, it's nice to fucking see the results of that. Where it's just like, that's very strange. But I get why, I guess I could see the argument there. They're kind of saying, like, as you're reading normally, you're reading from least significant bit to most significant bit. Now, when you see this extra bits case, you are now reading in a chunk. So I could see the argument maybe for the endianness of those two things to be inverted from each other. But yeah, that's crazy. That's fucking crazy. But I'm really happy with this. We've got to the point where we are compressing something with back references, and it's giving us the exact same thing as the real decompressors. So super sick. Super sick. I think I'm going to call it there for today. I think I might call it on this project as well. I think that, like, there is a level of we've kind of captured most of the complexity here at this point. The only thing that we're really missing is, like, dynamic Huffman blocks where they, like, encode the Huffman table and drop it in at the beginning of the block. But I don't think that that's, like, really worth. I don't think we're going to gain much info from decoding that, even though I just said that you think you get it and then you don't get it. But there's also kind of the part where I think this is kind of getting boring. And that's probably the bigger aspect of why I'm going to call here. So I think we'll be back tomorrow. And I think we're going to start a new project of trying to decode a QR code. Probably I'll stay in Zig because I want to keep going. I'm having fun here. So yeah, I think we're going to trying to do a QR code decoding from scratch tomorrow is what we're going to be looking at. So thanks for watching. We stream most days at around 2 o'clock Pacific time, so it's 4:30 now, so anytime between 2.5 hours ago and 4 usually. We usually don't stream for more than 2 hours, but today I wanted to get like tie a nice little bow on this before calling it. So a little longer one today. If you like what you saw, there's a YouTube link in the Twitch description and a GitHub link in the Twitch description. So both of those will take you to code for the projects that we're working on, as well as like previous projects. If you are curious about what's in there, there's like, operating system from scratch, neural network, some like 3D geometry stuff, like, kind of like our own shitty little game engine. What else is in there? Virtual file system, Git GUI, diff algorithm. There's like kind of like whatever the fuck I feel like doing, So if you're interested in any of that, that's there. If you can't see the links, it's just the same username everywhere. If you're watching on YouTube, there should be a Twitch link in the Twitch description, or Twitch link in the YouTube description. Feel free to swing by if you want to say hi. Other than that, thanks for watching, guys, and I'll catch you on the next one. Bye!